Thanks, Nir. Thanks, organize, etc. Can you hear me in the back? Should I? OK, great. When I get quieter and you stop hearing me, shout. Okay. Yeah, so this is some joint works. So it's mostly going to be a joint work with Amir, the first guy on there, and Ryan, the last. But it's some joint works with those people, some works of those people without me. But OK, so the first part of the child, distributed PCP theorem, is going to be a mystery for a while. Let me start with explaining what I mean by harness of approximation in P. So here is a flagship example. It's called the max inner product problem. You have two sets of vector in 0, 1 to the d. D is small, but bigger than constant. And you want to find A from A and B from B that maximize the inner product over the reals. Okay. And this is the embarrassing part of the talk. I have to apologize. There are two variants of this problem. There is the bichromatic variant that I just told you about. There are two sets A and B, and you have to find A from A and B from B. And there is a monochromatic version where you just have one set, and you find any two vectors, and you want to maximize the inner product. And in the original Fox 17 paper, we mistakenly claimed our theory also holds for the monochromatic version. This is a mistake, and I apologize for that. I mean, I claimed, and I convinced my co-authors to put it in the paper, so it's really my fault. The good news is that there is a really exciting paper that's going to be in upcoming ITCS by Kartik and Pasi Manurangsi that essentially fixes the problem, and it's beautiful, and you should all read it. And first open problem for the talk is, so you know, we submitted the paper. It's my fault. We submitted a paper with a mistake, and et cetera. And then a few weeks before the conference, we realized that we had a mistake. And I asked to change to add an erratum, change the paper, something, nothing. So open problem, especially the more senior of you here. Why do we still have published proceedings? I have no idea. Anyway. Back to PCPs, almost PCPs, sorry. So there is this problem. I want to find the... No, it's great, but why publish it, right? Just have the conference, right?
Even better, give people a thing that looks like the proceedings but doesn't have anything inside, so they can put it on the...
But yeah, and then you'll... Great. Yeah, so... OK, back to this inner product problem. So yeah, and we're going to focus on the regime where the sets A and B have a large number of vectors n, and but the length of the vector is some short d. And now there is a trivial algorithm that runs in n squared time, where you just check all the pairs, and for each pair compute the inner product and find the biggest pair. And the big open question is, or the big question I want to ask is, can we have algorithms that run much faster than n squared? So n to the 2 minus epsilon even for some tiny epsilon. And it turns out that no. So assuming this Seth hypothesis I'll define later, you can actually prove that you cannot beat n squared. And the original paper that did this, Ryle Williams in 2005, showed that if you want to solve this problem exactly, then you cannot beat n squared. You get truly subquadratic time. And 2016, there was a paper that showed if you want a very good approximation, that's still hard. But 1.01 approximation was open, 2 approximation, all of these were open. And just when there is a trivial algorithm, then you just look at one coordinate. So you cannot, a D approximation is trivial. So we know that red is bad, it's algorithm. So we know that you cannot beat red, and the question is, are we closer to this 1 plus log of 1, or almost polynomial? And our techniques allows us to get almost all the way to the upper bound, and there is even some improvement sense. Get really close. Okay. So that's now they're all excited about this. I'll tell you how we do this, and then we can talk later about other things that we can do with this new framework. By the way, there's I have no there is no punchline. This is the punchline. I guess there is nothing I have to cover in this talk. So please feel free to stop me with questions. Encouraged to stop me with questions. So before I tell you how to get the hardness approximation, let's see how we get the exact hardness, and then we can talk about hardness approximation. So the strong exponential time hypothesis states that, or postulates, that solving k-set for large enough constant k requires roughly time to the n if you have n variables. That's the best algorithm we have, and maybe that's the best possible. And now here's the reduction. So you start with a CNF phi, that's the input to the k-set with n variables. And now we define the two sets of vectors. So you enumerate over all the half assignments x1 to xn over 2, the assignment of the first half of the variables. And for each half assignment, you construct a vector A. And for each half assignment to the second half of the variables, you construct a vector B. And now you have some gadgets that guarantee that the inner product A dot B is large if and only if the half assignments together satisfy the formula. The punchline is that the size of the reduction is capital N, which is roughly 2 to the n over 2. And now if you plug that back into the strong exponential time hypothesis, you get that n squared, capital N squared lower bound. Questions?
Reduction size n is the number of
the number of vectors. So lowercase n is the number of variables, and capital N is the number of clauses. You see the length of the vectors is something that depends on lowercase n, so it's much smaller. Okay. And my goal in this talk is to show you how to get the hardness for a 2 approximation. And maybe if we have time, we can discuss how to extend this even beyond to like really hard hardness. Okay. So the way we like to prove hardness of approximation is the PCP theorem, right? The center of this workshop. And hopefully after 3 days of the workshop, you know that there are 2 ways to think about the PCP theorem. One is as a probabilistically checkable proof. So there is a 3-set phi in a satisfying assignment. And we want to write a proof such as the verifier only reads a few bits from the proof and can be convinced that the assignment actually satisfies the CNF. And another equivalent way is to, as hardness of amplification, you have a 3-set phi and n variables, and you construct a 3-set phi prime and n prime variables, such that approximating phi prime is as hard as solving phi, exactly. And for now, let's focus on the hardness amplification. We want to get the hardness approximation, and specifically on the trade-off between n variables and n prime variables. So the original proof of the PCP theorem, the dependence was pretty good. It was almost quadratic. And then Polshik-Spielman improved to almost linear. And Dinur's PCP is n times polylog, so really close to linear. And it's a big open question if you can get linear, say 10n. And those of you that went to Eli's talk yesterday about blockchain, there are some applications for, there where they would like really, really short PCPs. Anyway, suppose that we had this fantasy PCP with only 10n variables in the in phi prime. Let's try to see what happens when we combine that with our Seth hardness reduction. So the reduction size is going to be roughly 2 to the n prime over 2, so roughly 2 to the 5n, even if we had the fantasy PCP. And that doesn't help us at all when, even if you had it doesn't rule out any non-trivial algorithms. Okay. So now my goal is to tell you how to overcome this, and that's going to be with distributed PCPs. But before I talk about distributed PCPs, let's warm up with distributed error correcting codes. As you know, PCPs and error correcting codes are very closely related. So I have a message that I want to encode, and I give the first half of the message to Alice, and I give the second half of the message to Bob. And now Alice encodes her half of the message, and Bob encodes his half of the message. And I take the two encodings, and I write them next to each other. Turns out this is a pretty good error correcting code. So maybe I lose a constant fraction in rate or distance, but it's still a pretty good error correcting code. And now I want to do the same thing with PCPs. And for that, let's think of PCP in the other formulation. Let's think of it as a checkable proof. So I have a 3-sat phi that everyone knows. And then I have a satisfying assignment. I give Alice the first half of the assignment, and she writes some local PCP. I give Bob the second half of the assignment, and he writes some local PCP. And then you take the PCPs together, and hopefully it's a pretty good PCP for the claim alpha beta satisfies the CNF phi. The good news is that this completely circumvents the PCP blowup that I told you about earlier with the n and n prime. Here's why. So if you look at the reduction again, instead of constructing a vector for every half assignment, I'll construct a vector for the local PCP that I construct from the half assignment. So I have half assignment alpha, and I construct a vector for this pi of alpha. And then I construct a vector B for this pi of beta. And the gadgets guarantee that the dot product between A and B is approximately equal to the probability that the verifier accepts the verifier accepts alpha beta. That's a typo. It should be pi of alpha beta. So the pi of alpha, pi of beta, sorry. Anyway, the punchline is that the number of gadgets stayed the same. So maybe the PCP still stretches the vector, so the vectors are a little bit longer, but the number of vectors is the same, which is the bigger parameter here in the reduction. Okay. The bad news is that we actually can construct distributed PCPs. Okay. And here is a very simple 2-line proof of this. Okay? So if you're looking at this formula, it's actually a 2-sat, so a very easy CNF. And even simpler than that, it has a very nice structure. So for every I give Alice the input alpha, and I give Bob the input beta I, and I just want one of them to be no. And does anyone see under what condition do alpha and beta together satisfy this formula phi? What condition on alpha and beta? Okay, so some of you mentioned that it's on the slide. It's when alpha and beta are disjoint as sets, then they satisfy this formula, right? And now suppose that we had a distributed PCP. Then alpha and beta, then Alice and Bob can locally write their local PCPs. And then they can simulate the verifier and solve this set disjointness problem with very little communication. But we know that in communication complexity, set disjointness requires linear communication, even if you have randomized communication, even if you have non-deterministic communication. Okay. Now, before I tell you how to overcome this problem, let me just mention that the reduction goes both ways. So if you had any formula phi, then you can define two sets. So S alpha is a set of clauses that Alice's half assignment doesn't satisfy. And T beta can be the set of clauses that Bob's half assignment doesn't satisfy. And now if I have a clause in S alpha, I still hope that maybe, so I know Alice's alpha doesn't satisfy it, but I'm still hoping that Bob's half assignment satisfies it. And the clause is not satisfied if it's in both sets. In other words, all the clauses are satisfied if and only if the sets are disjoint. So this is exactly the set disjointness. Okay, so if I could only solve set disjointness, I would be in good shape. But like I said, set disjointness requires linear communication, which is a problem. And the way we'll overcome this is using a Marilyn Arthur or a Marilyn Alice Bob model of communication. So Marilyn is this wizard that he sees everything, but he's untrusted. So very much like the witness in the PCP theory in NP, but we also have access to randomness after we see Marilyn's advice. So this is the protocol. Marilyn sends Alice roughly square root of n bits. And then Alice and Bob toss some coins. And then Bob sends Alice roughly square root of n bits. And then Alice decides to either accept or reject. Okay. And I'll actually show you the protocol. And I think in this PCP workshop, this is maybe the simplest proof of anything that someone can call a PCP theorem in some way. So here's the protocol. Alice takes her question? I was just surprised. Oh, surprise. OK, yeah. OK. Questions? Anyone else? No? OK. So here's the protocol. Alice writes she has this 0, 1 vector, S alpha, and she writes it as a root m by root m square. M, by the way, is the number of clauses, which is without loss of generality, is roughly the same as number of variables. Okay? And Bob does the same. It just writes the 0, 1, and it just writes it in the square. And now Alice uses a low degree extension. So every line in the square, and every row in the square, you can think of it as the values of a low degree polynomial. And then you can write the rest of the polynomial. And Bob does the same. And now this is the setup, and now we can look at Marilyn's message. So this is what Marilyn does. Marilyn looks at the two tables, and he computes the entry-wise product of every every two entries in Alice's table and Bob's table. And now it's still a low degree polynomial. It's not root m because you multiplied 2 root m degree polynomials. You have a 2 root m degree polynomial. But it's still relatively low degree, so it's error correcting. And now what Marilyn does is he sums each column. And this final message mu is just the sum of each of the column. Okay? And now Alice and Bob are going to toss some coins. Specifically, they're going to pick a random column. And Bob is going to send the values on his column to Alice. And now in the final step of the protocol, Alice looks at her column, and she looks at the column she received from Bob. And she computes entry-wise the dot product, so the entry-wise product and then the sum. And she expects to see this value that she received from Marilyn. And now, if Marilyn sent the correct vector, then she will always accept. And if Marilyn was cheating, because of the error correcting property of low degree polynomials, then Alice has a good probability of catching the cheat. So this is the full protocol. There is this mu, which is the sum of the columns. And then Alice and Bob pick a column J. Bob sends Alice all the entries in his column J. And Alice verifies that what she got from Marilyn really is the dot product of Alice and Bob, of hers and Bob's vectors. Okay. And this gives what I call a non-deterministic and distributed PCP. So there is a CNF that everyone knows, and there is Alice's half assignment and Bob's half assignment. And there is a short hint from Marilyn. And now each of them writes their local PCP, but Alice's local PCP can also depend on the message from the hint from Marilyn. And now, so I can't tell you this guy's name, but it starts with a V. It's the verifier. He reads one symbol, so it's pretty large symbol, root n bits, from each of the Alice's local proof and Bob's local proof. And then you can output accept or reject. Okay. And now let's tie it all together and show you how to get a harness for the original harness approximation for this maximum inner product problem. So we're going to get a small number of vectors. The vectors are going to be pretty long, so D is going to be roughly 2 to the root m, which is not great, but it's much smaller than 2 to the m, which is the number of vectors. Okay. So for every half assignment beta, I construct a vector b beta, where I have the r is the result of the coin toss, and k is every possible message. And b beta at the rk location is going to be 1 if and only if this is actually the message that Bob sends given randomness r. And Alice's message is defined similarly. And at the rk location, it's going to be 1 if and only if Alice accepts given randomness r and message k from Bob. And now the dot product is exactly equal to the probability that Alice accepts in the Marilyn R in the MA protocol. Okay, you're asleep. I won't try to wake you up. I understand it's after lunch. But let me show you some other cool stuff and some open problems. Bless you. So there's a similar problem like the maximum inner product problem. And now we just want to find the closest pair of vectors, say in L2 metric. And again, there's a trivial algorithm runs in roughly n squared time, and we want to beat n squared. And the same result of Rand shows that if you want to prove it, to solve it exactly, it's hard. But now there are actually non-trivial algorithms. So if you run in time n to the 2 minus epsilon, you can get a 1 plus order of epsilon approximation using locality-sensitive hashing. And you can do even better. There's a Valiant's algorithm. This is Greg Valiant. And gets 1 plus order epsilon squared. And you can do even better. There's roughly 1 plus almost epsilon cubed time. Sorry, 1 plus epsilon cubed approximation using what's called the polynomial method. What about 1 plus epsilon to the fourth? I don't know. What about 1 plus a little of 1? So something that doesn't depend on the epsilon in the running time. Okay? So that I do know. So I can prove that there is some function of epsilon where if you want a 1 plus f of epsilon approximation, you cannot do this faster than n to the 2 minus epsilon time. Okay, so for every epsilon, there exists delta of epsilon, such that if you want 1 plus delta approximation, you need n to the 2 minus epsilon time. So you can get this like a parameterized subquadratic. And corollary of this, and the reason we care about those bichromatic problems, is that if you want to do this approximate nearest neighbor problem, so we're given the set A in advance, and you get to pre-process it in polynomial time, any polynomial time. And then I give you a query B from the second set. You need almost linear time to answer an approximate nearest neighbor query. Another cool thing that happens so the proof is along the lines that we saw earlier. You add in AG codes and the parameters get better. Another thing that's interesting about this model is that I told you that we can solve set disjointness with the Merlin-Arthur protocol, and that gives a distributed PCP. It turns out that there are other special communication models. I, at some point, understood what np.upp is. And there's quantum communication. It turns out that you can use quantum communication and get a classical harness. So if you want the classical randomized algorithm for this plus minus 1 max inner product, the quantum communication for set disjointness can give it in this framework. And it turns out it's not only set disjointness. For other problems, the gadget that comes up might be equality, and then you can use the randomized protocol. Or if sometimes you need more than set disjointness, like circuit set, and then you need a full IP protocol. Another very interesting problem is this LCS closest pair. LCS stands for longest common subsequence. So it's the stuff they care about in bioinformatics, where you have 2 long strands of DNA, and you want to find how similar. You want to find 2 very similar strands with insertions and deletions. And now we have a result that we can show that. Forget about strong ETH. You can think of the exact problem. So you want to find the exact closest pair or the exact nearest neighbor. And you can think of the approximate problem, where you just want to find an approximate closest pair or approximate nearest neighbor. And it turns out the approximation is as hard as the exact problem, with a slight blow up or some blow up in the length of the vectors. And just to show you how simple the proofs are in this distributed PCP framework, all you need to say is that the longest common subsequence, it belongs to the class NL. There is the witness is just the sequence that's the common sequence plus their indices. And you can verify this in log space. And this means that LCS has an efficient communication protocol in the IP model, where you can interact with Merlin multiple times. And then you have, instead of a non-deterministic distributed PCP, you have an IP distributed PCP. So another amazing problem is just longest common subsequence without the closest pair. So you just have 2 very long strings, and you want to compute the longest common subsequence between them. Sorry, so again, here there is it's a non-trivial, but a pretty simple n² time algorithm that we teach in undergrad algorithms. And what we can show is that, OK, sorry, so it's been known that if you're assuming Seth, there are no better algorithms if you want to solve the problem exactly. And getting approximate longest common subsequence is a big open problem. Okay. And what we can show is that if you had deterministic approximation algorithms, then you could improve some non-trivial circuit lower bounds. So while these circuit lower bounds are lower bounds that we all believe are true, we also believe that proving them is very hard, and we're probably not going to prove them by coming up with new approximation algorithms for longest common subsequence.
What kind of lower bound?
So it's a good question. I don't know. I don't remember the exact statement off the top of my head. And they keep getting better. So the lower bounds keep getting stronger. The lower bounds that you could prove with this experiment keep getting stronger. But it's even the stronger lower bound that we believe we can prove.
Linear lower bounds or superlinear?
I think it's bounded depth. Yeah. Anyway, it's not it's circular lower bounds that you believe are true. I mean, you don't. It's for circular lower bounds for very large classes like exponential time or something like that. So you don't expect to have a circuit for this class, but you also don't. It's a big open problem in circuit complexity. You don't expect to solve this problem. You don't expect to solve it at all, but definitely not with this by finding a new algorithms for longest common subsequence. And I think I'm done. Let me just mention there are lots of open questions, and specifically this longest common subsequence, approximate longest common subsequence, two long strings. If in the closest pair, those approximate nearest neighbor closest pair, we also have some hardness results for eddy distance, but the hardness result we get for eddy distance, which is a very hard metric, the best thing that we have is via the L1 or L2 metric, which is a much easier metric. So we expect it to be much harder, and we don't know how to prove anything there. And so on. And I'll give a talk in a few weeks here in the seminar, and I hope to talk about. So we tried for a while to prove harness approximation for those LCS problems, and we've been stuck for a while. And now it seems that the reason we're stuck is algorithms. So, and with that, thank you.
Any questions?
Could you say a bit more about the circuit lower bounds? Is it via the combinations kind of randomization results? How is that?
Yeah, so it's via the algorithms give lower bound kind of framework. Specifically, so there's actually a PCP involved here, right? You can do better diagonalization if you had better algorithms. And it's there's Ben-Sisson Viola, and there's Ryan Williams and Murray Williams, I think, is the latest. Does that answer your question?
Any more questions? Okay, so let's thank the other here.